Hello everybody. Today we're going to talk briefly about two different contact forces. Now if you'll remember, contact forces are simply forces that can only be exerted when the objects actually touch, when they make physical contact. Not like gravity, which is a field force or non-contact force. The first one we're going to look at today is called the applied force. And this is basically what we call any force exerted by a person, an animal, or an animate object like a machine of some sort. We use a capital F with a subscript capital A to represent the applied force exerted on something. Now, unfortunately for us, there is no special equation for an applied force like there is for gravity. If we want to find an unknown applied force, we have to use our concepts of equilibrium or non-equilibrium, depending on the motion, in order to find the unknown applied force. In fact, let's take a moment to do that. Here's an example. It says a crane lifts a steel girder such that its upward acceleration is 0.38 meters per second. How much force did the crane apply to the girder? Now remember, a crane is an animate object, so it's lifting the girder. All right? So the first thing we're going to do is we're going to draw a free body diagram, and this dot represents the object of focus, which is the steel girder. This is what the forces are acting on. So, what are the forces acting on the steel girder? Well, we're on Earth, so we know it has weight, which I will indicate with mg. We also know it has the applied force exerted on it by the crane in the upward direction. But now what we have to remember is this steel girder is accelerating upward, so there must be a net force acting on the mass of the girder to make it accelerate, to change the motion of the girder. So that means for there to be a net force, the upward applied force has to be greater than the weight. That is the only way we can have an upward net force. In other words, the weight will cancel out part of the applied force, but not all of it. So we know this must be true. The magnitude of the applied force has to be greater than the weight, because we are in a state of non-equilibrium here when we're accelerating. And don't forget, this acceleration is upward, all right? So the net force, the greater force, must be upward. Now, notice we have two opposite directions in our plane of motion. And by the way, there are no other forces acting on the crane. There's just those two. So we're done with our diagram. But we need to realize there are two different directions, two opposite directions in the vertical plane indicated here. They cannot both be positive, so we need to decide what sign convention we're going to use. Well, I don't see any reason why we can't let the upward motion, the upward direction that the girder is moving in, be the positive direction, which would make down negative. Now, notice we know two things. We know the mass of the girder and we know the upward acceleration. And we want to know what is the applied force in this instant. So let's take a look at our concept. We know that we have an acceleration. Therefore, the net force, which by the way is the sum of the forces that are acting on the mass, will make that mass accelerate. This is Newton's second law. Okay? So if we want to find the net force, notice we know the mass and the acceleration. We want to find the net force, all we have to do is say m times a. Then, in order to get the applied force, it's one of the forces being summed. So let's take a look. Actually, I'm going to use these two parts. Let's take a look at them. All right, so right here, we're going to sum the forces. We only have two. We have the applied force, which is in the positive direction, and we have the weight, which is in the negative direction. These directions are very important. The signs make a difference. The mass and the acceleration upward, which is also positive, is important. If the acceleration were downward only, we'd have to be careful. That would have to be negative 2. When we assign sign conventions, all vectors that point those directions must obey that sign convention. Otherwise, you're not going to get the right answer, okay? Now, so we've stuck in our signs. We're ready to plug and chug numbers, except I do want to do one thing. We're looking for the applied force. Let's take the mg to the other side. So we're going to get the applied force equals m times a. Take that to the other side. We end up adding it. Okay? So we're going to always start, when it's in non-equilibrium, we're always going to start with this and then derive our working formula. This is our working formula, and we have derived it. This is what they expect on the AP exam. You start with your basics, you start with your concept, and you derive your working formula. If you can't do that, you're going to have a lot of trouble on the AP exam. All right, so let's plug and chug. We get 2,000 kilograms times 0.38 meters per second squared plus 2,000 kilograms. If you wanted to factor the mass out first, you could do that too. 9.8 meters per second squared. So now we end up with, I think this one is about 760 newtons. And if you multiply 2,000 by 9.8, you get almost 20,000. I think it's 19,600. Not quite 20,000 because that's not quite 10. All right. Now add those two together. All right. And you get an applied upward force from the crane acting on the girder of 20,360 newtons. The applied force has to be this big so that when the weight, when the gravity cancels out part of this, you have this much left to make the mass accelerate. Okay, this is actually the net force because it came from m times a. All right, so the applied force minus the weight gives us the net force, which makes the mass accelerate. Okay. All right. So this is an idea of one of the ways that we can find an unknown applied force using our concept. In this case, the non-equilibrium concept. Equilibrium concept is even easier to use because in equilibrium the forces have to balance. So if you want to find an unknown applied force, you simply find the value of the force that's balancing it, and it's the same thing as the applied force. All right, now the second contact force that we're going to look at today, and we're going to only partially look at it, is normal force. Normal force. Now, I like to use, and this is perfectly acceptable on the exam, instead of using an F sub n, I like to just use a capital N, and this is an acceptable alternative way of indicating normal force. Now, there's a reason why I don't like to use F sub n, and here's why. If you use F sub n, people want to think that it's the net force, and it's not. The normal force is not a net force. It is a particular kind of force exerted a particular way, but it's not a net, all right? So I like to use a capital N so that it keeps down the confusion. F sub n tends to confuse people into thinking it's a net force as opposed to normal. All right. A normal force is a force that acts on an object from a surface, like a floor, a wall, a road, the ground. A normal force is also, and I'm going to put this in red, it's also always, not every once in a while, always, perpendicular to the surface. That's exerting it, okay? It's perpendicular to that surface. Surfaces push perpendicularly, okay? So that's why the horizontal ground pushes straight up, perpendicular to itself. An incline pushes perpendicular to the incline. A wall, which is vertical, pushes horizontally. Get the idea? Okay. Now, there is no special equation for normal force, just like there's no special equation for applied force. Isn't that sad? It'd be nice if there were one, but there's not. It always depends on the situation involved and whether you're accelerating or moving at constant speed or at rest. In other words, we have to do the same thing we did here. We have to apply the concepts. Now, we're going to skip this a little bit for right now because I want to talk about that and the example that goes with it in one lesson. It's a little different. So let's just get used to what normal force is first, okay? Let's look at example 6. In fact, we're going to be looking at the crane from example 5 and the girder that it sits down on a structural support. Now we want to know what's the normal force acting from the support on the girder, okay? So let's take a look. Now, we can assume that this support is horizontal, that it sets the girder on, like maybe it sets it down on two support beams, all right? So if we look at a free body diagram, and I can just dot in a little girder if you want. See, it looks like that, and then maybe you've got two support beams on maybe one on each end or something that's holding it up. The crane is set it there. We want to know what is the normal force acting from the supports. So first we have gravity pulling down, and then we have the normal force from the supports pushing up. However, how big is it going to be compared to the gravity? Well, let's think about this. What's the motion of the girder now that it's on the supports? Well, it's zero. There is no motion, so it's at rest. That means we are in a state of equilibrium. In equilibrium, everything equals out, everything balances, so the normal force here must be balancing the gravity. And there are no other forces acting, okay? There's no left to right or right to left forces. Nothing's pushing on it, so that's it right there. Nothing more, nothing less. And we know that these two magnitudes must be equivalent because we're in equilibrium. They must balance out. One cannot be greater than the other. If it was, there would be an acceleration. All right, so how do we find the magnitude of the normal force here? Simple. We know the net force must be zero, and that's because of equilibrium. So that means the normal force magnitude must equal the gravity magnitude. So all we have to do is say, if we go back up here and get our information, 2,000 kilograms for the girder times the acceleration due to gravity, and we get a value of 19,600 newtons. So if that's the weight, the gravity exerted on the girder, then that must be the value of the normal force to keep it from falling, to keep it at rest. Now, that's not so bad, is it? Okay, so what you are going to be doing is you are going to be practicing an assignment using either non-equilibrium or equilibrium concepts to determine normal force. We'll continue to look at applied force every once in a while, but it's not always there just yet until we get into little tougher problems. But I do want you to look specifically at normal force. So I'm giving you an assignment where you can just practice some very basic normal force computations and do your free body diagrams. Free body diagrams are very important. We're going to be doing them all the time now, and every time we have a new force to add into our list, We'll have a new force to add in to our free body diagrams. Okay? All right, I'll talk to you later. Thanks for listening. Bye-bye.